Hello. Today I would like to talk about what is the difference between refactoring and re-engineering of software and some other more concepts like engineering also. So engineering, re-engineering and refactoring, all of them. So refactoring, just remind ourselves, drops the cost of four things: comprehending the code later on when you read your code, it will be much easier to understand because you named nicely your variables and functions, and you separated the jobs into different classes or different organization and design, so everything is very nicely organized. So accommodating new features, of course, if this is easy, so you can easily accommodate new change, adding unit tests because it's nicely sliced, and doing further refactoring also will be much easier. Is upfront design possible? Can you think everything from the very beginning? There is an answer from Martin Fowler. He says, I found that design, rather than occurring all upfront, occurs continuously during the development. So we are human and we don't know everything. So when we are learning domain with our limited knowledge, we might make some decisions. Or because of the time pressure and other things, you don't know everything and you cannot plan everything. You think during that time with the given information you make the right decision, but later on some more inputs comes and your design needs to change because you need to add more stuff on top of it. So it is continuously during the development. So software is a living thing. Early decisions may have been good at that time, but the context changes, customer change, technology changes, regulation changes, people change, etc. So you need to jump into the bigger ball, but this means you need to redesign, rethink, refactor all of them. So how can we reduce the maintenance changes? If we have higher quality, this means we do less corrective maintenance, right? And anticipating changes, less adaptive and perfective maintenance. Of course, we need to be always balanced because we cannot do, and maybe customer wants this, maybe that one, and this one, and then you unnecessarily implement. Maybe customer only needs one of them, but you spend time to develop these two others and the right unit tests and maintenance, all of them. So unnecessary wasting time. So everything should be balanced. Better tuning the user needs, less perfective maintenance, regularly performance preventative maintenance, which is refactoring. So Professor Lehman's laws of software evolution is there is continuing change. A program, this is very important, that is used in a real-world environment must change or become progressively less usable in that environment. Because when you start using software, new doors are open and you can automate some of the other things you were doing handcrafted or some of the stuff, and then you want to improve this. When you try to improve this means change. So when you're doing change, the complexity will rise, right? As program evolves, it becomes more complex, and extra resources are needed to preserve and simplify its structure. So change comes and software becomes more complex. So you need to, these extra resources are, in this case, we are going to focus on refactoring and re-engineering and mention about the difference. So in practice, Lehman's law, existing software is often modified in ad hoc manner. Quick fixes, lack of time, resources, money, knowledge, all of them. Initial good design is not maintained. Spaghetti code, copy-paste programming. Dependencies are introduced, no tests. Documentation is updated if there is one, not updated. Architecture and design documents are not up to date. Original developers leave, and with them their knowledge. So active knowledge is so important. Even the documents are good, but if developers are left, those are on papers. So this is also really a great issue of software world. So a typical result of such practices, you will turn the software into decayed and junk. So software maintenance, this is really important. Software maintenance costs continuously increase. Look at this number. Between 50 to 75% of global software development costs are spent in maintenance. You have already known this. We talked about this before. But this is Up to 60% of maintenance effort is spent on understanding the existing software. This is interesting. I wanted to emphasize on this one. You may say why? Because when I'm teaching the software refactoring class, students want to do changes and then they want to improve stuff, but they don't spend enough time to understand what is going on. And this is not fun part. This is a little bit not a fun part, and it's boring part. But when you reserve your patience and you will say, okay, I will do 60% of my time, understand, read somebody else's code, make sense out of it, and then you plan how can I improve, and you spend only 40% of your time to improve and make real changes. So I always tell this to my students, and this should be your mindset. Otherwise, you will be impatient and you will not do any good because you don't know and you are changing something, and then it may cause worse. So let's focus on this. Up to 60% of maintenance effort is spent on understanding. So Robert Martin, or Uncle Bob, what he says in his clean code book. Indeed, the ratio of time spent reading versus writing is well over 10 to 1. We are constantly reading old code as part of the effort to write new code. Therefore, making it easy to read makes it easier to write. So this is important. This means out of 10 lines of code, you write 1, but you read 10 lines. So this is really important to reserve your patience when you are doing refactoring. Refactoring is not like a magical bullet and you touch and everything becomes nice. So there's a lot of mental effort, mental CPU time has to spend. What makes software hard to maintain? Unstructured and complex code, low quality and poor design, insufficient domain knowledge, predict future demands, change requests, etc. Insufficient and out of sync documentation. So naming conventions, commenting. Of course, you will talk about these things. Commenting also very important. Your code should be self-explanatory. The function names, class names, all of them nicely organized. If you are using comment, this means you really need to write the command. If you are writing command everywhere, this means your code has an order. And what does that mean? You are writing command because your code is so complex, to make it clear to understand. So this is another subject we can talk later on. Lack of regular preventative maintenance. You don't spend any time on refactoring. You just always code for new features, and things becomes very difficult to lift the weight of the building, and this may collapse everything. We cannot have these many stories on top of each other. Maintaining someone else's code is also very difficult. So Lehman's laws in a nutshell. Observations are this: code decay, most usable software must evolve or die. Code aging, as software system gets bigger, its resulting complexity tends to limit its ability to grow. Yeah, this is aging, and you cannot add new features, new muscles to it because of the code becomes too big and very complex. And our advice is need to manage complexity, find the source of complexity, do periodic refactoring, redesigns, and refinements, treat software and development process as feedback system. So these are some advice. So this is a nice graph. So according to Lehman's law, there will always be change. Do you want to handle it? No or yes? If you say yes, what will happen? If you say no, let's go this part first. You will have many duplicated code. This means you spread the germ several places. You may fix it, and you forgot these two, and then your code is becoming buggy. Complex conditionals, abusive inheritance, large classes, methods, there are so much things. So you are actually taking a loan on your software. You will pay back via reengineering or refactoring. Both is possible. So if you want to handle these changes, you might want to refactor, then implement the changes. Investment for the future, paid back during the maintenance. So you can choose either path, but this may cause code decay and other stuff, and this may speed up you. Sometimes in order to jump someplace, you need to go 2 steps back and then jump over here. So refactoring looks like you are losing time, but actually to leap and then do better and easier changes. You may have seen this picture, right? Good, fast, cheap. Choose any two. You cannot choose all three of them. People tend to want to have fast and cheap, but it's not gonna be good. And if you are, racing for the market, you want to just release your software and make the customer happy. At first, maybe you can do this, but what will happen? Technical debt. So this will cause a problem, and how can you fix it? With refactoring. But you can only choose two of them. This is one I like from Dilbert. Did you finish the software yet? No, I'm still paying off the technical debt from the last programmer you pushed. Technical debt. Yeah, I don't know what that means. Well, that explains a lot. So technical debt is very important. I'm moving on. How about re-engineering? Re-engineering is the examination and alteration of a subject system to reconstitute it in a new form and the subsequent implementation of the new form. So I'd like to a little bit jump ahead and come back to this slide 27 later on. Just want to show you this picture. Maybe you played the Super Mario. The old version is this, and it is written in Turbo Pascal. A new version is this one, and then it is totally refactoring. What is that? They abandoned the source Turbo Pascal. I don't know with the current game what they are using, but they moved into here. So old code base, they cannot use it, but the idea and then documentations, if there is, all of them is re-engineering. This is not a refactoring because you build the system ground up, but with the knowledge and experience you have in here. So going back to that slide, re-engineering means making fundamental changes to the code. Here are the three core methods of re-engineering. Porting. Programs are modified to work on a new hardware platform. Okay. And translation. Programs are translated from legacy language to contemporary one. In this case, the example we gave. Migration. Programs are converted from a legacy language to a newer dialect. Okay. So let's look at about refactoring and re-engineering. So you have Fortran 4 code, legacy code. If you want to port a new platform, migrate to Fortran 95, maybe talking about this, translating it to C. So this is called re-engineering because you don't use any of the code base here, or just updating and changing. Refactoring is you are just maintaining the code, eliminating some of the dead codes, removing them. If there is code duplication, you are just renaming variables, and maybe changing the code structure using some design patterns. Or if there's an over-engineering, you want to maybe simplify it. So there could be a lot of stuff. Refactoring to re-engineering. In reality, the process of dealing with legacy code often begins with refactoring and progresses to re-engineering. Refactoring, if you are going to use that technology, if you are happy with that, but it is not organized, your code and all of them, refactoring is that, you are applying that. But if the refactoring no longer is solving your problem, then you might want to do re-engineering. Refactoring is the preventative action for code decaying. Re-engineering is costly than refactoring. So there is another term for that. I will come back to this one. Actually, big refactorings or large-scale refactorings, we can call, this one is a re-engineering. Some people like to call redesign or rewriting or platforming, or re-engineering is a system large-scale refactoring, because technically you aren't changing behavior, right? External behavior. The business logic and inputs, outputs stay the same. It's only the design and implementation that's changing. So large-scale refactoring changes can be ugly. They can take weeks or months or years to complete, requiring changes to make many different parts of the code. Martin Fowler says, big expensive changes that carry a lot of technical risk. This isn't cleaning up code and improving the design while you are working. This is fundamental redesign. Going back to here, let's look at this picture. what would you do? This is about re-engineering, okay? These are all re-engineering. So this is low part, this is high. If the business value of a software, let's say this part, for example, this is high value and code base quality is high. So what do you do? No, right, what do you do in here? No pressure for re-engineering. This is cool. You don't need to do anything. And then if business value is low, but code base quality again still high, so you don't need to do any re-engineering. So the C will be here, right? And another thing is it is very valuable for the business, but the code quality is low, you may want to do re-engineering. And if this value is not, business value is low, code quality is bad, maybe you want to throw away everything and you want to rewrite everything because this is not, worth to invest time to do anything. So that's the picture we get. But of course, each of them debatable. You need to decide. You can make decisions based on your needs, but this is general outcome. Complexity. This is another view of the same fact. If the complexity high, frequency of changes high, high complexity, frequent changes, apply strategic refactoring. So if it is low complexity, but frequent changes occurs, this is good, no problem. And again, low complexity seldom changes, usually it's good for experiments. And this is less changes and high complexity, don't touch it, it says. So moving on, engineering versus re-engineering. Let's go about this. I'm going fast because I don't want to lose so much time of yours. Engineering is a process of designing and developing a new product, right? Everybody knows engineering. You design, there is nothing exists, and then you plan and you design. Re-engineering is the process of understanding and changing an existing product for various reasons. Usually you are re-engineering is a system that you did not develop initially. But let's look at, I'd like to go to a picture first and then come back to this one. So the re-engineering life cycle, you have code base over here, and this code base they have no documentation, you don't know the requirements, so you do reverse engineering from the code and then you get the requirements of the existing one. So from here you want to re-engineer and then you get the new requirements also on top of it, and then you design again and code, and you get a new code base. Let's say it is from Pascal, you move to the C++, C#, something like that. So there's a forward engineering. What is this arrow says? If you have the requirements and you develop and get to the code, this is actually regular engineering, we know. So this is whole things we call, this whole things re-engineering, all of them. It's a big refactoring, we can say also. Going back to here. Recognizing the need to re-engineer. How do you know when you have a large legacy problem? Common wisdom says if ain't broke, don't fix it. But let's look at this. From functional point of view, something is broken only if it no longer delivers the function it is designed to perform. From the maintenance point of view, however, a piece of software is broken if it can no longer be maintained. So that is, code is rotten, so decayed, so it's a problem. So symptoms when to re-engineer: lack of knowledge. There is no documentation, obsolete departure of the original developers, disappearance of inside knowledge, limited understanding of the entire system, missing test. This is lack of knowledge part. Process symptoms: too long to turn things over to production. So you want to have new feature, it takes 3 months to deliver. Need for constant bug fixes, maintenance dependencies, difficulties separating products. Simple changes take too long. Code symptoms: duplicated code smells, big build times. All of them are, it shows when to re-engineer. Also, other things: architectural problems, refactoring, opportunities. These are the stuff. So I'm just going to let you read this one. You can pause the slides. Just moving on to the next stuff. And we have already studied this one, what is forward engineering, reverse engineering, and re-engineering. Goals of reverse engineering. This is very similar stuff. Cope with complexity, generate alternative views, recover lost information. This is reverse engineering. Detect side effects, synthesize higher abstraction, facilitate reuse. What is in the picture reverse engineering? This one. You may have no documentation or less documentation, out-of-date documentation. You want to come to the requirements. So there are other pictures explaining the same facts from requirements. You do forward engineering and design from here to implementation. If we have the code, reverse engineering, try to understand the requirements. And if you want to redesign and re-engineer, and all of them goes in the picture. If you want to spend some time, you can pause this and study this one. Moving to some more details, and I would like to conclude this presentation. There is one another representation of this process, like what is architectural transformation from the re-engineering perspective of IEEEs. Very similar things. They have horseshoe model, so it is the same stuff explained in different wordings, but the very same fact. It's explaining the re-engineering. So re-engineering, you do reverse engineering, you do some changes, and then the requirements updated, and then forward engineering. This is all called re-engineering. So this delta captures alterations made to the original system, the formula. So moving on to the last slide. That's our. That's all. But this is, what is this? Re-engineering, or is this re-engineering or refactoring? So you do whatever you do to make the customer happy and continue to update and change what customer really wants. And I use these books, and some of the resources are under this slide notes. Thank you for listening. Have a good day.